Dear everyone, I'm deeply honored and truly humbled to be here and share my research works. It is a moment that fills me with both excitement and gratitude. I would like to express my sincerest thanks to the organization community for their recognition of my work. This award is not just a personal achievement, but a testament to the hard work and dedication of my colleagues, mentors, and the entire research team. Photodynamic therapy is a cancer treatment method which employs reactive oxygen species in suit generated by a photosynthesizer and oxygen under illumination to eliminate cancer cells. Photosynthesizers are activated by light with specific wavelengths to produce toxic ROS. Therefore, photodynamic therapy can selectively kill cancer cells at the elimination sites, resulting in reduced side effects and better tolerance as compared to traditional cancer treatments such as chemotherapy and radiotherapy. To now, photodynamic therapy is still severely limited by tumor hypoxia, high levels of intracellular glutathione, and insufficient photosensitizer uptake, and so on. In addition, photodynamic therapy worsens tumor hypoxia, which might cause the poor prognosis by inducing tumor angiogenesis. To address the limitations of photodynamic therapy, various strategies have been proposed. Here are our representative research works to develop novel strategies to potentiate photodynamic therapy. We prepared ICG-loaded hydroxyethyl starch oleic acid conjugate nanoparticles and rationally combined ICG-loaded nanoparticles with PITC for potent photodynamic therapy. By controlling the amount of OA in HSOA nanoparticles with a diameter of around 15 nanometer were obtained. After loading of ICG, the prepared ICG-loaded nanoparticles exhibit significantly enhanced stability as compared to free ICG. PEITC depletes intracellular glutathione significantly. Photodynamic therapy based on ICG-loaded nanoparticles combined with PITC synergistically suppress cancer cells in vitro. In vivo studies, ICG-loaded nanoparticles exhibit significantly enhanced tumor accumulation as compared to free ICG. As a result, ICG-loaded nanoparticles exhibit enhanced in vivo photothermal effect and photodynamic effect as compared to free ICG. In vivo and tumor activity study, ICG-loaded nanoparticles combined with PRTC show significantly reduced tumor progression. As compared to ICG-loaded nanoparticles under laser irradiation. ICG-loaded nanoparticles combined with PITC also show significantly reduced tumor progression as compared to PITC, indicating the synergistic tumor inhibition effect of ICG-loaded nanoparticles and PITC. This work shows that a combination of ICG-loaded nanoparticles with PITC represent a novel and efficient strategy to enhance photodynamic therapy efficacy. In the next work, we combine oxygen supply, glutathione depletion, and tumor targeting in one nano platform. Folate decorated mesoporous polydopamine FA-MPPD nanoparticles collided with new indocyanine grain RR 820 and PFO to overcome the photodynamic therapy resistance. The MPPD will react with glutathione by the microaddition reaction, resulting glutathione depletion. The reaction of MPPD with glutathione also promotes IR 820 release from the nanoparticles. IR 820 and PFO colloided MPPD nanoparticles and IR 820 and PFO colloided FA-MPPD exhibit enhanced singlet oxygen generation as compared to IR 820 loaded MPPD, suggesting that loading of PFO can further enhance singlet oxygen generation by supplying oxygen. In which autosomal study, IR 820 loaded MPPD, IR 820 and PFO co-loaded MPPD, and IR 820 PFO co-loaded FA-MPPD nanoparticles exhibit enhanced photothermal effect as compared to free IR 820. In vitro cellular uptake study, 820 loaded MPPD and IR 820 and PFO colloided MPPD nanoparticles exhibit 1.5 times higher cellular uptake amount as compared to free IR 820 and IR 820 and PFO co-loaded FA-MPPD nanoparticles exhibit 1.4 times higher cellular uptake amount as compared to IR 820 loaded MPPD and IR 820 and PFO co-loaded MPPD nanoparticles after incubation with HepG2 cells for 2 hours. After incubation for 6 hours, IR 820 loaded MPPD and IR 820 and PFO co-loaded MPPD nanoparticles exhibit 1.8 times higher cellular uptake amount as compared to IR 820 and IR 820 and PFO co-loaded FA-MPPD nanoparticles exhibit 1.2 times higher cellular uptake amount as compared to IR 820 loaded MPPD and IR 800 and PFO co-loaded MPPD nanoparticles. The results suggest that IR 820 and PFO co-loaded FA-MPPD nanoparticles can enter into HepG2 cells by folate receptor-mediated endocytosis pathway. The intracellular glutathione depletion effect of MPPD and FA-MPPD was studied by incubation of MPPD and FA-MPPD nanoparticles with HepG2 cells from 24 hour MPPD and FA-MPPD nanoparticles exhibit similar intracellular glutathione depletion effect and deplete intracellular glutathione in a dose-dependent manner. The results demonstrates the ability of MPPD and FA-MPPD to deplete intracellular glutathione. The in vitro and tumor activity study indicated that 820 loaded MPPD nanoparticles exhibit enhanced photocytotoxicity as compared to free IR 820, IR 820 and PFO co-loaded MPPD nanoparticles exhibit enhanced photocytotoxicity as compared to IR 820 loaded MPPD nanoparticles. IR 820 and PFO co-loaded MPBT nanoparticles exhibited the strongest photocytotoxicity. In vivo studies, free IR at 120, IR at 120 loaded MPBT, IR at 120 and PFO co-loaded MPBT and IR at 100 and PFO co-loaded FI-MPBT nanoparticles all exhibit rapid and significant tumor temperature rise upon laser irradiation, which are ascribed to the higher intratumoral IR at 120 concentration. IR at 120 loaded MPBD, IR at 100 and PFO, IR at 120 and PFO co-loaded MPBD and IR at 120 and PFO co-loaded FI-MPBD nanoparticles exhibit slightly enhanced tumor temperature rise as compared to free IR at 120, which is due to their enhanced photothermal response. IR at 120 and PFO co-loaded MPBD and IR at 120 and PFO co-loaded FA MPBD, but not free IR at 120 and IR at 120 loaded MPBD nanoparticles exhibit a significant tumor growth inhibition effect without laser irradiation, and IR at 120 and PFO co-loaded FMPBD exhibit significantly enhanced tumor growth inhibition effect as compared to IR at 120 and PFO co-loaded MPBD nanoparticles. Upon laser irradiation, free IR at 120, IR at 120 loaded MPBD, IR at 120 and PFO loaded MPBD, and IR at 120 and PFO loaded FA MPBD all exhibit significantly enhanced tumor growth inhibition effect as compared to the corresponding drug without laser irradiation. IR at 120 and PFO co-loaded FA MPBD with laser irradiation exhibited the most potent anti-tumor effect. Upon laser irradiation, free IR at 120 and IR at 120 loaded MPBD exhibit significantly enhanced tumor cell HIF-1 alpha expression, suggesting that photodynamic therapy worsens tumor hypoxia. In contrast, IR at 120 and PFO co-loaded MPBD and IR at 120 and PFO co-loaded FA MPBD exhibit low HIF-1 alpha expression and high intratumoral RS level upon laser irradiation, suggesting that the loaded PFO in IR at 120 and PFO co-loaded MPBD and IR at 120 and PFO co-loaded FA-MPBD nanoparticles could provide sustained intratumoral oxygen supply which boosts the photodynamic therapy effect. Moreover, IR at 120 and PFO co-loaded FA-MPBD exhibit enhanced intratumoral oxygen supply as compared to IR at 120 and PFO co-loaded MPBD, and more potent photodynamic therapeutic effect. In another work, we prepared curcumin-loaded reduction responsive project nanoparticles of new indocyanine green for synergistic cancer chemophotodynamic therapy. IR at 120 was first reacted with cysteamine to obtain aminated IR at 120. Then aminated IR at 120 was condensed with carboxylated methoxy PEG in the presence of EDCI and DMAP to fold IR at 120 conjugate. The curcumin-loaded conjugate nanoparticles were prepared by a thin-film hydration method. Both the conjugate and the curcumin-loaded conjugate nanoparticles display worm-like morphology. To better understand the self-assembly behaviors of and the structures of the warm-like nanoparticles, DVD simulation was performed. You can be seen from the final state of the simulation that there are multiple cores formed by IR-820 in the worm-like cluster, and the curcumin is loaded both in the aggregated PEG chains and cores formed by IR-820. Negatively charged IR-820 molecules are near to the surface of the worm-like cluster, which leads to the negative zeta potential of curcumin-loaded conjugate nanoparticles. The curcumin-loaded conjugate nanoparticles exhibit reduction-responsive drug release behaviors and suggest that the curcumin-loaded conjugate nanoparticles might effectively release the cargoes in the tumor cells while be relatively stable in the blood circulation. In vitro cellular uptake study, the curcumin-loaded conjugate nanoparticles exhibit 2 times higher cellular uptake amount of 820 and 1.9 times higher cellular uptake amount of curcumin as compared to the mixture of IR-820 and curcumin at 2 hours, while show 3 times higher cellular uptake amount of IR-820 and 2.4 times higher cellular uptake amount of curcumin as compared to the mixture of IR-820 and curcumin at 4 hours, further confirming the efficient cellular uptake of curcumin-loaded conjugate nanoparticles. The efficient cellular uptake of curcumin-loaded conjugate nanoparticles might be attributed to their special worm-like morphology, which has higher contact area with cell membranes. Curcumin-loaded conjugate nanoparticles and the mixture of IR-820 and curcumin have different biodistribution. Curcumin-loaded conjugate nanoparticles exhibit significantly reduced liver accumulation and enhanced tumor accumulation as compared to a mixture of IR-820 and curcumin, suggesting that curcumin-loaded conjugate nanoparticles might effectively escape from the capture of reticular endothelial system in liver and preferentially accumulate in tumor by the enhanced permeability and retention effect. In vivo studies, IR-820 and curcumin mixture group show significantly decreased tumor HIF-1 alpha and VEGF protein expression levels as compared to PBS group, and then curcumin-loaded conjugate nanoparticles group display lower tumor HIF-1 alpha and VEGF protein expression levels. The results indicate that curcumin-loaded conjugate nanoparticles exhibit enhanced HIF-1 alpha and VEGF suppression effect as compared to the mixture of IR-820 and curcumin. In vivo anti-tumor activity study, both curcumin and IR-820 exhibit weak tumor growth inhibition effect. The mixture of IR-820 and curcumin exhibited slightly enhanced tumor growth inhibition effect as compared to curcumin or IR-820. Curcumin-loaded conjugate nanoparticles exhibit significantly enhanced tumor growth inhibition effect as compared to the mixture of IR-820 and curcumin. The CD 34 immunofluorescence staining results show that curcumin, IR-820 and the mixture of IR-820 and curcumin groups all display significantly decreased neurovascular density as compared to PBS group, and curcumin-loaded conjugate nanoparticles exhibited the lowest neurovascular density, suggesting that curcumin-loaded conjugate nanoparticles effectively inhibited the tumor angiogenesis. This could be ascribed to the efficient suppression effect on HIF1 alpha and VEGF. HIF1 alpha VEGF signaling can induce resistance to photodynamic therapy through promoting angiogenesis. Therefore, the effective inhibition effect of curcumin-loaded conjugate nanoparticles on tumor angiogenesis could bolster the photodynamic therapy efficacy, resulting in the synergistic anti-tumor effect. Collectively, these results indicate that curcumin-loaded conjugate nanoparticles effectively inhibit the tumor angiogenesis, which potentiates the photodynamic therapeutic efficacy and leads to the best anti-tumor effect of curcumin-loaded conjugate nanoparticles. This work provided a novel and relatively simple strategy for synergistic console camera photodynamic therapy. Here are my representative publications in recent years, including the materials studied by International Journal of Nanoscience, Journal of Colloid and Interface Science, European Polymer Journal, Nanoscale, SS Applied Materials Interfaces. Thank you.